We'll continue switching systems. Design for m greater than n. If a three-stage concentrator has m incoming trunks and n outgoing trunks, its primary switches each have m inlets and its tertiary switches have n outlets. Then number of primary switches are m by m and number of tertiary switches n by n. If there are G2 secondary switches, then cross point for primary switch is m into G2. The cross point for secondary switches equals m by m, n by n. Cross points per tertiary switch is G2 into n. Total number of cross points is C3 is equal to m by n into m G2 plus G2 m by m, n by n plus n by n into G2 into n. If you take G2 as common, m plus n by m, n by n. Since m is greater than n, let the number of A links is equal to number of B links is equal to n. So G2 into m by m is equal to G2 into n by m. Hence G2 is equal to n and m is equal to n, m by n. Substituting this, C3 is equal to m plus n into n plus n square by n. Differentiating with respect to n to find minimum gives m is equal to m by square root of m plus n is equal to n by square root of m plus n. C3 is equal to 2n square root of n plus m. Design a three-stage network for connecting 100 incoming trunks to 100 outgoing trunks. That is, a square root of 100 by 2 is equal to 7.07. Use n or n is equal to 10. So if n is equal to 5, there are 20 primary switches of size 5 into 5 and 5 secondary switches of size 20 into 20, 20 tertiary switches of size 5 into 5. If n is equal to 10, there are 10 primary switches, 10 secondary switches and 10 tertiary switches, each of size 10 into 10. Therefore, number of cross points C3 is equal to 2 into square root of 2 n to the power 3 by 2. C3 is equal to 2 into square root of 2, 100 to the power of 3 by 2. So, we'll get 2028 cross points. So, approximately we'll take it as 3000 cross points. So design of three-stage network for 100 incoming trunks and 400 outgoing trunks. Therefore 100 divided by square root of 100 plus 400 is equal to 4.47. So 400 divided by 100 plus 400 is equal to 11.89. M is equal to 4 or M is equal to 5. N is equal to 16 or 20. If M is equal to 5, N is equal to 20. There are 20 primary switches of size 5 into 5. 5 secondary switches of size 20 into 20 and 20 tertiary switches of 5 into 20. If m is equal to 4 and n is equal to 16, there are 25 primary switches of size 4 into 4 and 4 secondary switches of size 25 into 25 and 25 tertiary switches of size 4 into 16. So C3 is equal to n square root of n plus m 2 into 100 plus 400. 200 into 22.3 for 4460. Say we can take it as 4500. Four-stage network. Four-stage network can be constructed by considering a complete two-stage network as a single switch and then forming a larger two-stage array from such switches. Figure shows four-stage network for 100 incoming and 100 outgoing trunks constructed from two-stage networks of 100 inlets and 100 outlets using 10 cross 10 switches. So figure shows four-stage switching network of 1000 incoming trunks and 1000 outgoing trunks using 10 cross 10 switches. If a network has n incoming trunks and n outgoing trunks, then the number of cross points per incoming trunk for a single stage is proportional to n. For a two-stage network, it is proportional to n to the power of 1 by 2, and for a three-stage partially interconnected network, it is proportional to n to the power 1 by 3. Thus, for the networks having many trunks, it is economic to use more stages than for network with fewer trunks. These networks are only distribution stages. There is only one path between an incoming trunk and an outgoing trunk. If more paths are needed to reduce blocking, mixing stages should be added. For example, by changing a two-stage network to a fully interconnected three-stage network or changing a partially interconnected three-stage network T-stage network to a 4-stage network. Consequently, the design of a large switching network involves providing distribution stages to obtain cross-point economy and mixing stages to reduce blocking. It is rarely possible to use switches of exactly the optimum sizes. Also, the cost of switches is not exactly proportional to the number of cross points. For example, doubling the inlet and outlet capacity of a crossbar switch requires 4 times as many cross points but only twice the number of magnets. In addition, the complexity and cost of associated control equipment increases with the number of stages. Consequently, many switching networks use fewer stages and larger switches would be indicated by the equation.